This is a question from the Open Intro book. It is believed that nearsightedness affects about 8% of all children. In a random sample of 194 children, 21 are nearsighted. Conduct a hypothesis test for the following question. Do these data provide evidence that the 8% value is inaccurate? Recall that a proportion is a kind of sample mean, so the central limit theorem applies. The sample proportion should have a normal distribution. Its mean will be the population proportion. Its standard deviation will be the square root of p times 1 minus p divided by n. Our null hypothesis is that the population proportion of nearsighted children is 0.08. P equals 0.08. Our alternative hypothesis is that it does not equal 0.08. This is a two-sided hypothesis test because we're interested in whether it's different from 0.08, not specifically greater than 0.08 or specifically less than 0.08. We've got a sample of 194 kids, and 21 are nearsighted. So our sample proportion, p hat, is 21 divided by 194. When we're doing a two-sided test, we look at where the statistic shows up. Then we calculate the more extreme area, then find the corresponding area on the other side. In this case, the test statistic, p hat, shows up above the hypothesized proportion at 0.08. The values that are more extreme than this would be the area ahead of p hat. And because it's a two-sided test, we incorporate the same area on the other side of the distribution as well. The p-value will be this area here. The area ahead of p hat is 1 minus p norm, p hat, 0.08 for p, and then the standard deviation term. And we multiply that by 2 because we want the area on the other side as well. And the p-value is 0.147. If we want to do a hypothesis test in one direction, we calculate the p-value from the area in one direction. If our alternative is that the population proportion is greater than 0.08, then we only care about this area here. And the p-value is half what it was before. But we still fail to reject at the 0.05 level. If our alternative is that the population proportion is less than 0.08, then the area of the p-value is this. And that's because values more extreme than what we got would be anything lower than p hat, according to our alternative hypothesis. The direction of the test is determined by your alternative hypothesis. And now here's an example of drawing a normal confidence interval. The way we go about it for proportions is kind of complicated, so I'll get to that later. Today, I'll show you how to do it for a population mean when you know the population standard deviation. 1.96 is the 97.5th percentile of the standard normal distribution, and negative 1.96 is the 2.5th percentile. 95% of the area is between these two numbers for a standard normal distribution. And I explained the derivation in the lecture. The bounds of our interval are going to be the sample mean minus 1.96 times the standard deviation divided by the square root of n, and the sample mean plus 1.96 times the standard deviation divided by the square root of n. We are 95% confident that the population mean electric consumption is between 997.28 and 1052.72 kilowatt hours. A confidence interval is an inverted two-sided hypothesis test. At the 0.05 level, we fail to reject the null hypothesis because 1000 is inside the interval.